Here we go. Record. All right. So I have no idea what lecture it is, by the way, and all these holidays and the pandemic and whatever. So who cares at this point? We're in week 13 of a 16-week semester. And anyhow, so today what we do, we start what is typically called vector calculus. So sort of to set the stage, to remind you of what this might mean, you might say, well, we've been talking about vectors. And I agree, we've had some vectors pop up here and there. But what we haven't done is we haven't thought of it in this particular way that we're going to do today. So to sort of motivate, recall the types of functions you're familiar with. So I guess I can write that as we know. Now, of course, when I say no, I'm not saying you're an expert at this. What I'm saying is, hey, these are the functions that you've been studying since you first started discussing what a function is. But what now we're going to do is we're going to kind of write it in a more professional, more mathematical way. So the first type of function you study is functions that sort of take a real number into a real number. That sort of look like, you know, y equals f of x. So what does this mean? Let's write it in sort of in a more descriptive way. What this means is we input a number into f, and it returns a number. So what's an example of this? An example of this is something like f of x equals 3x plus 1, you know, g of x equals x squared, you know, h of x equals sine of x cubed minus 4x, etc. You guys get the idea. These are the functions you spent most of your math education from high school on studying. Now, you know, obviously some of you who've taken, you know, classes in programming or maybe some other math classes, your notion of a function is more abstract, which is not wrong. That's correct. It's just what I'm talking about is from a math standpoint in just algebra and calculus. These are the types of functions that we've talked about. So once you study these guys, then we graduated to what we called vector valued functions. Does anybody have a question about this at all before I go to the next slide or board? Okay,
actually,
so yeah.
Computer scientists have been adapting to the math way of functional programming.
Well, that's like the big thing now, Haskell, right? Isn't that sort of, I see some of the nerds yapping about that.
Some are, but yeah, there's certain functional programming languages.
By the way, listen to my new project. You'll probably think it's easy, but the fact that, well, let's pretend that you're all 21. The liquor stores are closed. And so if you want to order alcohol in PA, you got to go online and get lucky because the website doesn't always let you order. So I'm in the process of writing code that allows me to randomly, every so often, go to the web page and determine if it's letting me buy liquor or not. See, this is the skills that I found. It's actually doesn't seem like it's that hard to do.
Is it like a lottery thing?
No, it's not a lottery. They claim that they only open it up randomly throughout the day. So it's not like maybe it's an IP address lottery. I don't know. Maybe they randomly select a county every hour and let people from that county or that, you know, who knows how they do it. They're not very open about it.
Interesting. Yeah, that had to be really easy.
Yeah, it's not hard to do. I found it's amazing what the internet can teach you. All right. including calculus. Okay, so the next type of function we learn, we'll switch colors for the heck of it. Next, and you really don't learn about, we do this briefly in Calc 2, but mostly this semester. So next, you study functions that take a number, but spit out either 2 numbers, 3 numbers, 4, which we usually wrote in terms of a vector. So let's say, we can say r to the power n, where n is some positive integer. So in our class, in here we studied the case n equals 2 and 3. So what did these look like? We wrote these like this. We might have something like this, or we might have something like this. So, we called these so we gave a name for their graphs. We called them like space curves. And or trajectories. So this is, again, we studied this, in the case of 2 and 3, the output. So what you're seeing here is the input is a number and the output is a vector, either in 2 or 3 dimensions. Now, you could imagine that this can generalize to any dimension, but we're looking mostly for examples that kind of come at us from the physical world, and the physical world is, in the most basic sense, is 2 and 3 dimensions. Now, of course, we can argue there's some people use more, but we're just babies right now, and I say that in a loving way, as you guys all know. So we did calculus on these things. We talked about the derivative and how we can interpret it as a velocity vector, and we talked about these tangents and normals, the length of these curves, and the applications. Okay, then the next things we studied was the opposite. So then we studied what we call scalar functions. Or scalar valued functions. So that's kind of the technical jargon for these guys. These would be, and by the way, let me go back to the previous page. You might say you wrote f up here and then wrote r here, but again, it doesn't matter what the name of the function is. What matters is what is the input and what is the output. So the name is, as you guys know, I can use any letter to reference the name. So maybe I should have written, if I want to be more consistent with my notation, is not to confuse you, I could write R here instead of, and I'll put an arrow above to illustrate that R, you give it a number and R associates it with a vector. Hence that little arrow above. Okay, so what we did next is we studied functions that were scalar valued. That means it takes on a vector. You input a vector into it and it spits out a number. And once again, what do we care about in this class? We cared about the case where n was 2 or 3. But of course, you could generalize it to any number of cases. So what were some examples? Well, the example would be something like y equals f evaluated at xy, or we talked about w equals f evaluated at xyz. And what would be some specific ones of these, you might have like f of xy equals 4x squared y plus the sine of x. So these are examples of functions where you gave it 2 or 3 numbers and it spits out one number. And these had, we were able to do calculus on these things. We were able to talk about what's the largest number it spits out, what's the smallest number it spits out. We were able to talk about integrating these creatures. We were able to talk about, you know, taking derivatives and all that. We kind of spent some time doing, and we sort of exhausted, you know, what we might do in a one semester with these types of functions. So then the obvious place to go then, and this is what we're heading at right now, is the following. So the only type left to study are what we might call, I'm going to use capital F because that's standard. We want to take functions, and I'll put an arrow above it to emphasize that it's going to take a vector and it's going to spit out a vector. Now notice I used 2 different letters here. I used N and M because the idea is, in general, you might give it a vector of 2 inputs, but it might spit out a vector of 13 inputs. You might give it a vector of 3 inputs and it might spit out 47. So in this class, we restrict N and M to 2 and 3. So these functions have a name because they are functions, are often called vector fields. And hopefully we'll see why that's an appropriate name soon enough. So before we go any further, does anybody have a question? Okay, so let's just note again for full completion. So the input is a quote unquote vector, and output is a vector. Now you might say, oh Grady, why are you writing vector in quotations? Well, again, this is that mathematical maturity that I've been talking about since the beginning of the semester. One of the things that is very important, and I harped on this day one, is that in many ways, structurally, a point in space can also be thought of as a tip of a vector. We've talked about this. And so when I use the word vector, you know, you can imagine that I could be talking about an arrow who starts at the origin and whose tip is at whatever those coordinates are. Or you can imagine just a point at those coordinates. Or you can even also imagine that if I write the vector 1, 3, you know that there are infinitely many vectors 1, 3. I mean, the vector 1, 3 just means I go to the right 1 and up 3. So I can place the tail of that vector, the tail at any point that I want. So we talked about this a few times throughout the semester, and we even use terms like sometimes we distinguish between a vector and a position vector so that we know where the tail is placed. And so what you guys have to remember is that context is the key here. And that is just something that comes with experience. Does anybody have a question about this? Okay, so sweet. By the way, some of you are probably familiar with what we would call a vector field, even though you didn't think of it that way. If you ever took a physics class where you talked about electric fields or magnetic fields, and anytime an instructor has ever drawn them with arrows, or maybe you're talking about 2-point charges coming at each other or repelling, how do we mathematically describe that? We use what are called vector fields. Okay, so let's look at a couple examples before we do anything. So suppose I had something like f, and I put like x comma y. I'm going to take on 2 inputs, and maybe it spits out the following. So that's one example of a vector field. Let's do one in 3 dimensions. Perhaps we have cosine of x, e to the 4xy, and then 5z squared. Here are 2 examples of what we might call a vector field, or more abstractly, a function from R2 into R3, and then a function from R3 into R3. Now, knowing what you know, one of the first things that we do when we're teaching not necessarily young people, I shouldn't say that, when we're teaching students about graphs and the very first types of functions in graphs, is we want you to notice that you can visualize a relationship using a graph. And when you're in pre-calculus algebra courses, you know that you can draw an XY axis and you can see the relationship. And then when you get to Calc 3, you realize when you have more than one variable in and out, it's much more difficult to visualize these relationships because of the amount of dimensions that these graphs live in. Think about it. If you have a function of one variable in the one variable, its graph lives in 2 dimensions, the plane. We also saw that if you have a function from one variable into 3 dimensions, its graph lives in 3-dimensional space. We saw that a graph from, say, 2 inputs to 1 number, that's how we got these surfaces. So their graph also lives in 3-dimensional space. So what that tells you then is that a vector field, say that it takes 2 inputs and spits out 2 inputs, that tells you that its graph would live in 4 dimensions. And none of us can visualize that. But there is a very useful way of visualizing these things. Much easier in 2 dimensions than in 3 dimensions, but we can do it. Before we do any of that, does anybody have a question? Okay, so let's motivate it like that. How can we visualize these creatures? So perhaps the best way I can get you to think about it would be to use things from the physical world. So the first thing I would do is first think about physical examples. So what I'm going to do on the next page is write these down. So the first one I'm going to give you is the following. Each one of us is sitting in some place on the surface of the earth, correct? Now, from the looks of it, everybody except maybe Austin, maybe he's outside and he's playing with us. But the looks of it, we're all sitting inside. But if we were outside, we would notice the following. So at heavens to Betsy O'Grady. So at any point on the surface of the earth, there is a wind. Let's put it like this, a wind with a speed and direction. What's this thing? Right? I mean, you could go outside right now and then you might say, well, it's not windy. And I would say, okay, well, then the speed is 0. But likely if you went outside at any given time, the wind is going to be blowing, and it's going to be blowing at a certain speed, and it's going to have a certain direction. So we can have a function that assigns each point on the sphere, that's Earth, a vector, and that is the wind, speed, and direction. So maybe that is, what's the point on the sphere? Well, it has an X, Y, and Z coordinate, and it spits out some vector. Maybe we'll call it little f of X, Y, Z, and then little g of X, Y, Z. And then what's another one? I don't know. How about little h evaluated at X, Y, Z? Does anybody have a question about this example? Again, go outside. The wind is blowing. It's blowing at a speed, possibly 0. And it's also blowing in a direction. You can think of that wind as a vector. And you can think of the input of the function as whatever position on the sphere, the Earth, that we live. Each point on the sphere is assigned to a wind speed and direction. That is a function that inputs 3 numbers and outputs 3 numbers. Another example is, imagine a river or stream. So at each point, so just here's our river. Let's imagine it's flowing. So let's not say at each point. Let's formulate it a little more naively. What you can do is pick any point, say a molecule, and look at its speed and direction. So imagine you're standing above, you're looking down on, say you're in a helicopter looking down on a river, and you say, okay, just pick any point, or think of a molecule, or imagine you drop some flotation thing. Maybe you take how about you take a beach ball and you say, I'm going to drop it in the river. What are some things you're going to notice just intuitively? Well, if you drop it in the middle of the river, it's going to move faster. If you drop it closer to the bank of the river, it's not going to move as fast. Now, these things are all dependent on how wide and deep and all that stuff. But either way, if you look at that ball, you can measure its speed relative to, say, you measure its speed relative to the riverbank. You can also measure what direction is it going. Is it moving parallel to the riverbank? Is it maybe moving in towards the center? Is it moving out? So you can imagine that at each point in time, you are associating a direction and speed with that particular beach ball or that molecule. So what these two things are, these are physical examples, and let me just give you one more from physics. You could say electric and magnetic fields. So all of these can be what we say modeled by vector fields. And you would imagine that the reason that these things are called vector fields is precisely from the historical context. Where do you think these types of functions first arose? When people were studying things like fluids, and people were studying things such as magnetic and electric fields. In fact, much of what we're going to do the rest of the semester, all this math was essentially discovered, if you want to say it, or invented, however you want to think about it philosophically. It was either discovered or invented to answer questions about things such as electricity and magnetics and things such as fluids. We're going to study some big theorems towards the end of the semester by the names of guys like Green and Stokes. And these were scientists who were trying to answer questions about fluids and electricity and magnetism. Does anybody have a question? Again, I'm just trying to give you some motivation. Now, is this a complete job at it? Absolutely not. I mean, we're sitting here, I'm sitting downstairs in my house, and I'm trying to write on some little tablet so that I can best help you guys learn. This is not the most ideal situation, but there's plenty you can read about this. I am just trying to give you some examples to think about. I would really encourage that you think about it. And then, it might give you a little less difficulty when we start doing some math. Okay. Does anybody have a question? So another thing you're familiar with, even though you don't realize it, is the following. Important example. Given a, and we're going to start using these terms more and more, given a scalar function, say phi goes from R3 into R. Its gradient, of course, if it exists, is a vector field. So that is, anytime you have a scalar function, you can take its gradient. Don't forget what that is. That is the partial with respect to x, the partial with respect to y, and the partial with respect to z. That is, in fact, a vector field. So there's a very natural vector field that's always living there. Okay, now let's think about this. Imagine you had a scalar function like we did. Take any surface that we can draw. Go draw a surface in R2, or whose domain is R2. Go to GeoGebra. Now think about this. Take any point on that surface and you have your partials. These are like the tangents in each of the coordinate directions. And so what you can visualize is that at every point on that surface, there are arrows. Each one of those partials, if you take that gradient, that is a vector. So at every point on that surface, we can associate a vector. Now, what I can't do, well, I guess I could, but we should probably, the learning experience would be much better if you did it, is if you take a simple surface like, x squared plus y squared, or you took 1 minus that, the paraboloid, and then you went and computed some of the gradient at a couple points and graphed those on GeoGebra. And then you're starting to visualize how we could visualize a vector field. The best way to visualize a vector field is just take, whether it's a region in the plane or it's a region in 3 dimensions, and at every point you draw an arrow. So let's think about this. So what the above does is it gives an idea how to visualize a general vector field. So here's what I mean by that. So if I take a vector from R2 into R2, we can draw a vector, in particular, the output vector, at each corresponding input. So the best way for me to show you how to do this is to just do a specific example. So that's what we're going to do. We're going to take a very simple vector field and we're going to try to visualize it. And again, I would like you to keep physical things in your mind, like how do we study fluids moving? How would we mathematically represent fluids? How would we mathematically represent wind directions and speeds? How would we mathematically represent a magnet or gravity? How would we mathematically represent the fact that everything falls to the earth when it's close enough because it's being pulled by gravity? So think about that when we're doing these things. So let's look at an example. So let's take something that's pretty straightforward. And by the way, the best way to do this is to use technology. And there's plenty of software that's out there for free that will help you do this. And we're going to show you that in a second. But let's do it by hand because that's the old-fashioned way. So let's take the following vector field. I'm going to input two numbers. This is much more difficult to do in 3D. And what I'm going to do is I'm going to output something. What am I going to output? I'm going to output the following. So to get a feel for this, let's plot a few, or not plot a few, let's compute a few. Uh-oh, what's happening? So let's say I'm going to plug in 0, 0. What does that spit out? That spits out the vector 0, 0. By the way, notice I'm being very consistent with my notation. What did I tell you way back at the beginning of the semester? I said when I draw parentheses, I want you to interpret it as a point. And when I draw these things, I want you to interpret this as a vector. Even though abstractly they're the same thing, I need you to think of it as I'm inputting a point and I'm outputting an arrow or vector at that point. So what if I put now 0, 1? When I plug 0, 1 in, this spits out 0, 0. If I plug in, say 1, 0, it spits out the vector 0, the x input, which is 1. If I plug in, say -3, it spits out the vector 0, -3. And so in general, here's a very important way of thinking about it. If I take, it doesn't care, this input doesn't care what my y is. No matter what my y is, it's always, y doesn't affect the output if you pay attention to that. So no matter what I put in for x, it's always going to be 0, c. So in particular, the output doesn't depend on y. So what does that mean? That means all our outputs, if we think of them as vectors, they are not going to be tilted left or right because they have no dependence on the y. Or excuse me. Let me rephrase that. They're not going to move, they're not going to be tilted at all. They're either going to be an arrow pointing up or an arrow pointing down. And the reason that's the case is look at the output. The output has the x coordinate is always 0. So that tells us it doesn't move left or right at all. The output only moves up and down. So if we wanted to visualize this, what we could do is we can draw an xy axis. And at every given point, let's just plot a couple of these. So, we could think of this as 1, 0, and then this is -1, 0. And then you might have, so what are some of the points we evaluated? Well, we're going to say, okay, let's get a color here. When I plugged in 0, 1, what did I get? When you plug 0, 1 in, you get nothing. But what if you plugged in 1, 1? Well, in that case, I got a vector. And so what we notice is that all the vectors on this guy have the same length. Now I can't draw all of them, but I can try to represent them because I can't draw one at every single point, but I can try to represent them. Now, as I move further to the right, the x values increase. And that means that, again, don't forget what we have here. It's worth writing this down. So no matter what you put in for your x, I'll call it C. What happens is, as C increases, as x increases, the y coordinate of your output grows. So that, how do we represent that? How can we show that to the reader? Well, that just means as I go out to the right, the vectors are actually longer. And then similarly, if I look at the negative, it's going to be the opposite because they're going to be minus. They're going to be going down. By the way, this guy has a name, and maybe if you've heard of this word before. So this is often called what's called a shear field. So as I suggested earlier, the best way to teach yourself how this stuff works is to save your, you should do some of these by hand. But all you have to do is just Google vector field plotter or vector field grapher. GeoGebra does it. So what I'm going to do is I'm going to share a different page with you. Let us do, let's go to new share. So here's a built-in GeoGebra app. Hopefully, do you guys see this? You guys see the GeoGebra? Shake head, yeah. So what was our vector field? Well, the first component was just 0. And then the y component, or the second component, was x. And so you'll see this GeoGebra app is trying to do what I did. It just does it way better than I do, right? Now, here, let's think of maybe a physical world where this could be, this might be a model, or this might try to explain. This is called a shear field, and this kind of stuff can be used to understand how certain winds behave. And you could Google this and read about it all you want, but imagine we're trying to, maybe we're in a laboratory and we're studying something. We have a wall and we have wind going this way or air moving this way on one side of the wall, and I'm visualizing the y-axis as the wall, and then air coming the other way. And one of the things you might notice is that the molecules would be, the arrows that are smaller represent maybe it's moving slower because it's closer to friction of the wall. Just like you might imagine if you have fluids moving, you have one channel of water and then you have another channel of water back and forth. Maybe you have pumps pumping water one direction and the other direction. Oh, okay. Oh, good. Okay. Again, I'm not saying that everything is modeled or that this is a great model. I'm saying this is one option for, oh my God. That's Mommy. Don't call her Amy. My kids are nuts. Welcome to work from home, baby. Does anybody have a question about this? This is what it is. Austin, you can laugh all you want. Anthony, I should ship their asses over to your house. That's what I should do. You can babysit them today. Okay, let's look at some other examples that you might notice in the real world. Here's another one that's quite useful. If you do this, it's been shown many times in experiment that fluids behave a certain way. Here we go. So how do fluids behave? Let's check. Let me move this down for a second. I'm gonna kill something. Whoa, no. Ah! I'm hitting the wrong button. Give me a second. Ah, it's changing. I don't want it to change. All right, this is fine. So one of the things that we notice how fluids behave is that fluids move slower closer to their boundaries than they do not. So imagine, for example, you have blood flowing through your artery, or you have water moving through a hose. Experiment tells us that it's not going, that there's actually, you can calculate the speed, how it changes from close to the boundary, close to the center, and it's actually quadratic. That's why you see this 1 minus y business. And so what you're noticing, what is happening? Lydia, what is happening? I'm just kidding. Sorry. What you're noticing is that the arrows close to the x-axis are small. First off, this needs fixed. I don't know why this is spitting out the wrong thing. Let me reset this. I think it's being confused. Okay, so here's what you notice. You notice when something's wrong. We're skipping this example. It's not working right on this. Let's find another one. Something's wrong. Let's see if the Desmos one is any better. Oh my God. So the first function, what do we want? We want 1 minus y squared. And then we want, there we go. So what we want you to imagine, and again, this one, why is it doing this? Hold on, I'm trying to figure out why this is doing what it's doing. I have crying upstairs. All right, I'm getting some. This is doing something I don't want it to do. So now I'm gonna just do what we can do until I figure it out. Is we'll just do another example. I don't know why I was doing it. Okay, so here's a vector field that you can imagine is useful if we're trying to study, say, how something that rotates behaves. I want to change the size of my arrows. So you can imagine something that rotates. Maybe you're looking above, you're trying to model a tornado or a hurricane, or you're trying to understand how maybe fluids will go down a drain, anything that rotates. Now the length of the arrows, which I can't change because I don't know why. There we go. The length of the arrows is there to describe us that. The speed, the length of the arrows is to help us understand that the longer the arrow is, perhaps the faster it's going. Whereas the smaller the arrow is, the slower it's going. So this is what we often call a rotation field. Does anybody have a question about this? All right. So again, what's the big thing? And that was that wasn't the greatest explanation. I feel bad. I should have tested one. I was having issues with that second example. I don't know why. Prior proper planning, I suppose. Anyhow, uh, uh, if we go to the next page, we can show you what we mean by that one, and we'll draw a quick picture. And hopefully you can go play around with this. The next one we want to do would be, how do we get it to look like it rotates? Well, we get it to look like this. And so if we draw, or if we define it like this, then at every point in the plane, we're associating an arrow that goes to the left, negative y, and goes up x, or down, depending on the sign. So how would I encourage you to think about this? You should try to draw a couple of these. When you plug 0, 0, and you get nothing, so it's 0, 0, there's no vector. So let's see. I got an idea. If I plug 0, 0, and I get nothing, but suppose I plug 1 0 in. If I plug 1 0 in, that's this point, I get this guy. I get a vector that goes 0 left and right, but it goes up 1. And then if I plug, say I plug 1 1 in, then I get something that's tilted like this. And then if I plug 0, 1 in, I get this. And so what happens is you end up getting these rotations. And the further away you move from the origin, the longer the arrows become. Does anybody have a question about this? I mean, these are obviously very tedious to draw by hand, but it's worth your while to try it, to get a feel for it, and then use technology to do it. Does anybody have a question about this? There's two other important examples that we should talk about, or it's a more general one. So let's just mention that real quick. So things like gravity and electric charge sometimes are modeled this way. So we call these radial fields. So this just looks something like this. You know, we know what the length of, so if you take any vector and divide it by its length, raised to some number, what you end up getting is you get the following. You can get, and you probably have seen a little bit of this, you know, maybe you saw it in a physics class. You might get something that looks like this. Or something that's the opposite, and I'll draw this in a second. So you could get everything that sort of pushes away from the origin, or you can have things that are coming towards the origin. So imagine like an electric charge that's, repelling or, attracting. Or you could imagine something like the center of the earth pulling everything towards it, a gravitational force. Does anybody have a question about this? Going once, going twice. All right, so the first thing you need to do is you need to get a handle on working with these things. So what we'll do on Friday is we'll start talking about some integration and most importantly, some of the more useful physical examples are we're going to want to integrate. I guess we could say it now like it's not completely correct, but we sort of want to integrate a vector field. So imagine this physical problem. Imagine that you want, imagine you want to know the flight path of sort of a bird flying. And what you want to do is you could integrate to determine that flight path. And then you might have another question. You might want to know how much work is done. How much work does it require the bird not to just fly a certain path, but through a certain wind field, if you will. Now, as you guys know, if I'm running into the wind, it's a little more difficult than if the wind is behind me. So you would imagine that something swimming in water, the amount of energy or work required is going to be dependent on what is the current of said water. If I'm flying an airplane, do I want to go against the wind? Do I want to go with the wind? How does that affect things such as fuel efficiency? So how do we begin to even think about these things? Well, one of the ways is we can imagine an object moving through some vector field, and we can ask how much work is required by that vector field, or how much, I guess you can rephrase it either way by Newton's laws. And the way we do that is through integration. So we'll talk about that on Friday, but we do want you to get some work, practicing drawing vector fields, or at least visualizing them, and go get a favorite vector field application. I mean, Wolfram probably does. I bet you they have a good one. Theirs is probably the best one. I don't know why. Let's see. Built-in functions. Let's see. I don't know. I'll have to figure it out. Look, they do have one. Let's just show you real quick. If you just Google, I figured they would. If you just Google Wolfram vector field plot, you can do it. So we look at the one we did before. We did the one rotation. Here's another one. So if we want to rotate the other way, we just flip the sign, and you get this rotational field. Does anybody have a question about this? Oh, by the way, how do you get the length? If you want to get something that's radial, all you do is just divide it by its length. So if I just do x, y, if I just compute whatever I get that plugs in, notice these are all arrows that go away from the origin. Maybe we have a charge that's repelling. Anyhow, we could talk more about the math on Friday. I think we should leave it here because, well, we can't really start the integration now because we won't finish it. Give you some time to maybe, I got to post an assignment for you. Maybe you can practice this stuff. Find a web page that is good. Does anybody have any questions before I stop recording? All right. You're smiling. You're growing your mustache. This is real good, Austin. All right, I'm going to stop recording.